Okay, so please, in computer operation, we had already established that there are only three processes that happens in computer operations. You have the input, you have the process, and then you have the output. Now, the input many times are what the user presents to the embedded system or to the controller to act on. For instance, if I want to design a surveillance system that alerts me when somebody, maybe a burglar system. I want to know when somebody intends or tries to break into my house through the window or through the door. What I will need to do is to have some set of sensors that can place it on the windows, at the door, or somewhere around where the person might intend to come into the house through. That will be an input system to the controller. The work of the controller will then be based on the instructions I've written to say, when it happens that the sensor is breached, or when it happens that the sensors monitor, senses, or picks up any of those interactions for which it is designed to pick up, please do so and so thing. Those processes happens within the controller. The output should then be, oh, put on an alarm, shoot a gun, send a text message, send me a notification somehow. Now, that will be a complete system. You now have the input, you have the process, and then you have the output. Now, so what I've actually been doing, or what our classes have been based on since we started, is learning basic syntaxes on how to interact with the controllers to carry out some of these things I just said. And sincerely, we've been very much on processes since we started. We've learned processes and outputs, actually. We've learned how to increment. First of all, we've learned how to actually create registers within the controller. We've actually learned how to write values into the register, how to increment the content of the register, and how to output the content of that register on a given port or pin on the microcontroller. So the assignment that I gave last week was this. I said, I want us to design an up and down counter. It means that we are going to be bringing in two input buttons. One button will be to increment, the other button will be to decrement. Now, so the essence of the class was this. We said, let's design an up and down counter. A system with which when I press a button, a given register within the microcontroller is incremented or decremented, and the value latched on an 8-pin port or an 8-port pin of the microcontroller. That understanding will help you be able to replace those buttons with sensors. And that we had already established last week. We did that last week. We interface the microcontroller board with a PIR sensor, a passive infrared sensor. In that class, we discussed the difference between the passive infrared sensor and then I think the infrared proximity sensor. We had both at the office last week, and we worked with both. We saw how both works when it is being interfaced with the controller. All of that, maybe when either of you meet those who were in that class, it'll be easier for them to actually relate some of these things. So let's go into the assignment I gave. The assignment was to design an up and down counter. And as usual, we start with a circuit diagram. So what I'm going to be doing this morning is to design a circuit diagram. So I'm going to show you through the process of designing a circuit diagram, and then the programming aspect, the testing, the simulation, and then we can then go into the other businesses we have for the day, based on how much time we have on our hands. I'm going to share my screen right now so that we can start from there. So I'm going to share my screen, share the screen. Okay, so that's it. So first of all, as it is our custom, we will create a folder. So on my desktop, I'm going to create a folder. I'm going to call that folder assignments. So that's the folder. Now, in that folder is where I'm actually going to create or store the project files. Project files will mean the circuit diagram, the circuit diagram file, and then the software files. So I'm going to start with the circuit diagram file. So I'm going to go to where I create the circuit diagram. We use Proteus, and every one of them already have Proteus installed on their PC to start with. So I'm going to put up Proteus. Now when Proteus loads, I'm going to go to my schematic. Okay, I'm there right now, my schematic capture. And then I will start with adding component to my screen. First among the components I'm going to be adding will be the PIC 16F876A. That's the IC we've actually been using. It's a 28-pin microcontroller. The next I want to pick a crystal auxiliary capacitor. So I'll pick crystal. I know I'm going to need two 22 picofarad capacitor. All of these are standard things that we are actually going to need. All of these things are things I've actually talked about in the class. Now, I know that I'm going to need buttons. So I'm going to need buttons. So I'll go look for buttons. I picked on the active button. In connecting my button, either as active high or as active low, I'm going to need a 10 kilo ohms resistor. So I'm going to pick on resistors. I'm going to need a 10 kilo ohm resistor, a quarter watt 10 kilo ohm resistor. I know that, of course, I'm going to need a 390, 330 to maybe 470 ohm resistor, depending too, because of course I know I'm going to need that. I know I'm going to need light emitting diodes. I'm going to need LEDs. These are just standard components that we have actually been making use of. I could have started from an existing project, but I wanted you to see the process we go about it. I like to bring in everything on the LED, the yellow, the red, the green, and then the blue. I like to do that. What else am I likely going to need? I'm not sure. Maybe I'm going to need a bar graph LED. To electronics, I'm going to need a bar graph. So this is a bar graph display. I'm going to prefer, let me see, I'm going to prefer, okay, the green. Let's see, the green to the red. I'll prefer the green. Let's just bring that in too. And then what else are we going to need, Steven? We've already have a button. We can, okay, let's end it there. And then if we need anything else, we'll come to it. So let me begin. Now, I already have my components selected. The next thing I want to do is now arrange these components on my workspace. That's the next thing I want to do. So I start with the microcontroller, very important. I go for my PIC. Where is it? PIC 16F876A. Now, if you look at my screen, now the next thing I need to quickly do is to save. Anything can happen. So I'm going to lead it to where I actually created the folder assignment, and I'm going to actually name this class, this workspace, or this project workspace assignment to. So it helps me. And I saved it in the folder I created on my desktop, titled or labeled assignment. Now, I like my screen to be a bit big, so I can go to systems, I go to my set sheet size, and I can just make it smaller. It's actually on A4 right now. It's on 10 inch by 7 inch, so I can just pick 7 by 5. That's the user defined, so I can always change the value here to suit. Now, you see the workspace is now a bit small, and then what I have on the screen can be, it's a bit bolder than it was before. All right, so the next I want to do is, first of all, like we already discussed, for the microcontroller to come on or to be made use of, you need to actually give it VDD, which is your 5 volts. You are going to need to also give it your VSS, which is your ground voltage. You are also going to give it the oscillator pin, which is your oscillator 1 and 2. Those are the ones on your pin 9 and 10. Your master clear reset on pin 1. We already established that this microcontroller has 2 VSS. I believe they should be on pin, I'm not sure what pin they are on here, but I know they should either be on pin, I think 8 and 19 or 8 and 20. I'm not so sure. But that is on the physical layout of the board. On this microcontroller, that's on the physical layout. The VDD should be on pin 1, I'm not sure. That pin 1 also should be on pin 1. No, the master clear reset is on pin 1. I'm not sure where the VDD should be on pin 20. The VSS should be on pin 8 and 19. 8 and 19. Okay. So, but here we don't need any of that. All we need is the master clear reset to put it on. So I'm going to get a 10 k ohm resistor. I'm sorry if I'm a bit too fast. These are things we have actually covered already. Okay. So I'm going to bring in my. Yes, I know. So I'm going to bring in my 10 k ohm.
Go back and rewatch them.
Okay. All right, and I'm going to bring in my power, and then I'm going to connect my power to this microcontroller. So this is satisfying the power requirement of this controller. Alternatively, I can actually have this rotated. I think it kind of makes sense this way. And then this can come and stay here, and then I can place this here. And I save. Okay, so this is supplying it with its power requirements. The next thing I want to do is to give it the oscillator. Also very, very important. So I'm going to go back. I'm going to pick my crystal oscillatory capacitor. This is the crystal. I'm going to rotate the crystal a bit. We have a crystal fixed somewhere here. You come here, you stay here. I'm going to fix. Okay, I'm going to fix the crystal here. Fix the other end of the crystal here. Because of this pin, let's move this man a bit off. All right, I'm going to get my two starting capacitors, my 22 or 33 picofarad capacitors. I'm going to have it fixed here, this connected together, and then I'm going to get my ground and I'm going to place that here. And then this way, I would have satisfied the oscillator condition to power this controller on. The oscillator we've been using has actually been 20 megahertz, because the reason now, issue is that we can actually use any value of crystal oscillatory capacitor from any value available to 20 megahertz. But we already have an experimental board we are working with. Steven, I believe you come across the experimental board, and this is the oscillator on that experimental board. For the sake of the man who is just joining us, let me show him quickly what that experimental board is. I think I have it somewhere here. OpstepE. Okay, I think this is it. This should be the experimental board. So if you look closely, we already have a 20 megahertz crystal on that experimental board. So this is the crystal. Okay, so our design, because eventually for those who have been attending the class, this is what we are actually using to do our experiment. So if we are going to be designing any circuit diagram on our simulator, which is Proteus, we should be tailored towards fitting this board. Share with me. All right. And for those who already have it, the IC on this board is the 16F, the PIC 16F876A. The oscillator there is 20 megahertz, and the ceramic capacitors are 22 picofarad. So that is actually what I'm basing the circuit diagram I'm drawing it on, because this is where we are eventually going to flash the code in. Okay. All right, I just needed to say that. And so for IO, this is what the experimental board looks like. This is it. I don't know, but this is what the experimental board looks like. If in case you want to have it, you can actually have it. It's available at the office for pickup whenever you have the finances.
No problem.
Okay. All right. So back here. So that is why this crystal oscillatory capacitor is going to be 20 megahertz, and I can quickly double click on the controller and change the processor clock here from 1 megahertz to 20. Again, that is satisfying the external crystal value, and what we should feed into the system, into the controller. Okay, now so the next thing I'm going to do right now is to actually put up my buttons. Where is Steven? Okay, maybe we'll join us again. Okay, so let me continue. So the next thing I actually want to do is to bring in my buttons. Now, we had already established too in previous classes that our button can either be active high or active low. Now, it doesn't matter which of the configuration you choose. It doesn't matter. So, but to put up any of the configuration, what I will do is, again, I'm going to need, if I was to use an active high, which means the input of the controller should be defaultly low, and then it is when the button is pressed that it should go high. What I'm going to do will be this. I'm going to need a button. I'm going to rotate the button. I'm going to need a button. On the button, before the button will be my power. We have my power connected here. Then I'm going to need my resistor, the 10Q ohms resistor I needed at first. I'm going to have it here, connected here. And then I'm going to need to bring in ground. I'm going to bring in the ground voltage, which of course will be the negative of our power supply. We'll put that here. And then I can choose any of the pin I intend to use. For my my input, I might intend to use my arrow is 0. Now, don't forget, the idea of the assignment is to design an up and down counter. So I want to press a button, and I want a count to be incremented, a register to be incremented, and I want to actually press the button, another button, and decrement the count. So I'm going to need 2 of these. So I can just right-click on this, and then I highlight this configuration, and then I go and do block copy. I can have another one here. Very simple. And then I can decide to use my arrow 5 as the next input. I can have that come this way, come here, and I can have this. Please, does it make sense? Ayo. Is Ayo there? Okay.
Can you hear me? I don't know if it's my network or.
Yeah, it was the network. The network went off before. All right. Okay. So the next thing I'm going to do, now I have 2 buttons. We can choose to use this as the increment and use this as the decrement. So I can just maybe get something, get a label, and just text and write it. Oh, IO2 is off. The guy is back. Oh, okay. So I can just put increment and come here and put decrement. All right. So when I look at it, I know that this is for my increment, and I know this can be for my decrement. It's not compulsory. It's not just one of the things we can do to make your circuit diagram readable and understandable, irrespective of how long it's taking you to be off it. Now, are you there, Ayo? Okay, so the next thing I'm going to do is to decide if within port B or port C, which I would have loved to make my output port. All right. So I'm going to pick port B. I'm going to pick port C. I prefer to pick port C. So what I'll do is I'm going to go back to now. What the essence of the project is to increment a variable and then display the content of that variable on the port. So that the circuit diagram is not rough, I might just go for the bar graph, and then I'm going to place the bar graph here. I'm going to place the bar graph here. Let me zoom this out so that connecting it will not be difficult. Okay. So I do this, I do this, I do this. Then I can then bring in my 392 resistors. Then one is going to be here, another will be here, another here, another here. Now I could just highlight this, block copy, it makes it a bit easier. Okay, I think that's it. So all right, get there. Oh, get there. All right, and then the next thing I'm going to do is to bring in my ground again. So I'm going to bring in the ground, and I'm going to connect here and connect everyone to ground. This to ground, this to ground, this is to ground, this is to ground, this is to ground, this is to ground, and this is to ground. Okay, so that is our circuit diagram right there. Okay, so this is what the circuit diagram would eventually look like, or this is what the circuit diagram that you're actually supposed to design for the assignment I gave last week is supposed to look like. So the next thing we're going to do now is to then go to our compiler and then write a code that would respond when this button is pressed, and increment a count, and then when this respond also when this other button is pressed, and then decrement the count, and then display the content of the variable we're actually incrementing and decrementing on our PortC. So that is what the project is simply to do. So the next thing I'm going to do is go to my compiler and kickstart my compiler. We'll be using the PIC. So I'm now on my compiler. So the next thing is to take you guys through the process of setting up the workspace or the program workspace for this particular project. So I'm going to go to File. I'll go to New, and I'm going to go to the project wizard. Quickly, I'll go to my desktop where I have assignments, and I'll name it assignments. Okay, that's done. I'll save it, and then I'll come to the family. I'm going to pick PIC 16. I'm going to scroll down to where I'm going to get the PIC 16F876A. Okay, should be closed now. This is 876A. I'll leave the crystal clock speed to 20 megahertz. I'm going to come down to pins. I could make all my port A inputs. So any of the pins on port A can be used as inputs. I like to do that. And then I'm using port C. So I come down to port C and make all port C outputs. Now these are some of the features that the compiler affords us as against setting them by ourselves in our trace registers. So if the compiler affords us the possibilities or the flexibility, why not take advantage of it? So this is it. So I'm using all my port C as what as output. Again, another thing it offers you is label. We can change or we can label those. You can create labels instead of using the hash define within the environment of your compiler. You actually do that here. From our circuit diagram, we already set that our ROA is going to be our decrement, our ROA 5 is going to be our decrement. So we can actually do that here too. So we're going to come to ROA 5 and say U are the increments. We'll change it and say U will be the decrement button. And then we can come down to our fuses now and say power up timer. That's all. Okay, put protect from read if you want that. And then you can then say what create the project. And voila, here you have your project. Quickly is to compile. When you do, it's going to make available to you 2 additional files. The other file for the project you've created, which of course is the assignment.h, and then the IC you are using, which is the 16F876.h, which is of course is the header file for the IC you are using. Now, other fuses that are not set can actually be copied here and added to your H for those that it didn't create. If you look at it, these are not the only fuse options that you're supposed to set up. It only brought in 1, 2, 3, 4, 5 here, and I think there are more than that here. For our crystal, it didn't send on our crystal. So what I will do is I'm going to copy this and then rewrite the fuse. I'll just do that. I think it's something we should do. Let me take you through the process of doing that's not difficult. I can paste this here. Now we know that we are using 20 megahertz, so we should be using the HS. We don't need the ROC and then the XT. I don't want to watchdog timer. I want my power up timer on. So remove this. No brownouts. Yeah, no brownouts. I also don't want low volt. No low volt programming. I don't want that either. So I can do this quickly, and then you can do your code protect if you want. You can tell it no write protect to the stage to this point, and then tell it no debug either. Okay, so that's it. All right, so that of course one more last thing. You can then bring in your project and then remove the no project. All right, so that's it. Then compile again to be sure I know errors there, and then it tells you build successful. You have used 1% of your RAM size, and is 0% of your ROM size. So as we continue to actually add syntaxes to this workspace, we will continue to increase the RAM size or the ROM size of our controller. Okay, so I haven't done that in the age. And again, look at something that it did for us. It has given a name to our pin A0 and our pin A5. So this is the decrement, this is the increment. And then so you see how that comes to play when we come to using it. Okay, so this is the C. So what do I do here? Like every project, I also forgot to do that. Like every project, it's actually important that you have let me go back to the circle diagram. For every design, it's very important that you have one pin that is actually your power pin. Always very important. That is there to signify that your project is working. That is there to signify that your code actually started well. As against having an LED attached to your power supply. It's important or it's good that you have that around either or any of the pins on your microcontroller. We've already established that in the several classes we've had in class. So what I will do is I'm going to bring in again, so bring in my my 392 resistor. I could just have it on my ROB1, and then I'm going to have one of the light emitting diodes. I prefer the blue, and then I could put that here, and then take that, and then connect that to the ground source here. And so this will form our power LED. So don't forget, it's on ROB1. So I can come here, just as it has done this for me. I use all of this, so I can just copy this. I could just copy this. Okay, so what I just did was brought in port B. I think I wanted only port B1, so I could just change this to B1. All right, so that's using port B as output, and I can actually use my height define too here, as it's been done here, and say height define ROB1 and call it the power LED. Let's call it the power LED. Okay. All right. So if I rebuild, of course, there shouldn't be any error here. Then okay. Oh, that's me rebuilding again. Don't mind me. And then I'm going to go back here, and then I can start my project. So the first thing I want to do is to be sure that the power LED came on. So I'm going to say output a high on the power LED. What I would have written there would have been output underscore a high, open brackets, pin underscore B2. But since the B2, pin underscore B1 has already been ascribed the name power LED, there will be no need calling pin underscore B1 anymore. So I'll just call power LED. If I compile this project and then I go back to my my simulation environment, which is Proteus, and then I double click on the Proteus to add the project file. It's called assignment, and I say okay, and I save that. If I ask it to run, I expect this power LED to come on while others stay off. Now you see the power LED on. So this, of course, is just to show that our project or our system is on and running. We've not written anything for the port C. We've not written anything for the port A that has our increment and decrement buttons. We only have 4 power LED, and this is just to show that the power LED came on. So this is the first set of the project we've written, or the first thing to do. So this is just to show that the project is working. So back to our compiler. So what's the next thing we want to do? Next thing we want to do is to begin to see how we can scan for those input pins. How do we scan? Within the while true, what we should then do is to say if. Now don't forget the way we've actually been doing it. Let me go back to the way we've been doing it. You can quickly create a variable unsigned int. We could call that counter, and then we're going to initialize the counter to 0. So just say counter is equal. So I need this equal to sign here, or equal to, and then yeah. So counter is equal to 0. Unsigned int 8 space counter equals 0. So I can come here and then say, then I can create another one. Let me create another one, please. And I can call that W. So I'm going to come here and I say W is equal to input pin. Now I could say pin underscore A5. Well, since I'd already given it a name, it's increment. So I could just do this. There's it. The next thing I'll do is to say if W is equal, what are we scanning for? We're sensing for a 1. We'll do this.
Sorry, you equal to the have two. Like, does it matter?
Yes, it does. This is how you test if something is equal to something. It is not an assignment operator. This is not like saying W equal to 1. This is W equal to. That's the difference.
Okay.
So if you look at the line 9, this is saying W equals to something, or that all of this instruction is equal to W. That is what this is saying. That's what the line 9 is saying. The line 10 is asking, is W equals to 1? So that is asking a question. So this is how we do that here. All right. So, okay. So that is that. So W is equal to input pin underscore A5. So this is for the increment. So this is what we do, and then we do this. What I'm going to do quickly is to replicate this for the decrement. I'm going to do the same too, but this time I'm going to do it for the decrement, and I'll ask the same question if W is equal to 1. Now, on the increment, what do I want to do? What do I want to do? I want to increment a counter. So I can say counter plus plus. So I can say counter. There's my plus. Hey, not working. Okay, coming. Do I have anywhere I have plus here? Nowhere. Okay, so where's my on-screen keyword? Okay. Hold on. Okay, so I can get that now. So where was I? Okay, counter plus plus. All right. Okay. So the assignment was to count from 0 to 100. So our count should be between that. So counter plus plus. So the next question will be if counter if counter again is equal to 100, is equal or greater than 100. That was what I was going to ask for. Let counter not counter counter. Let counter equals 100. Okay. All right. Otherwise, that is it. So after incrementing, what I would do, This is a label way of writing this. Will be to output on port B the content of counter, and then it gets us of that loop. Now, when it comes to the decrement, we'll do the same thing. In the decrement, what I wanted to do is counter minus minus, and decrementing the content of that counter by 1. The next one I ask is if counter is less than 1, or okay, or is not working yet. So let's get this. Or counter is greater than 100, then counter should be equal to 0. So that's that. And then when it's done doing that, what it should do is to output on C the content of counter. Yeah, I think I said B. So this is C. All right. So and then
the output, the second one is in plural. Does it matter? Like, is it crucial? Okay.
Thank you very much, Ayo. Then I can compile. Now it's saying that in numeric, what is it saying? Okay, now this is not complete. It needs to close this and close this. All right, I think we're done now. All right, so that is just the project. So that is simply it. What I've actually done there is to bring these two instructions into a repetitive loop and test the content. So first of all, I check for the input of the state of the pin we have labeled to be our increment, which is pin underscore A4. The content should be written into W. If W is 1, of course, the only time that place is going to be high, the only place this place is going to be a 1 is when this button is what? Is pressed, either this or this. And then when it's 1, that is written into W. So the next is to test is W equals to 1. If W is equal to 1, increment this counter, this variable called counter by 1. And the test, if counter is greater than 100, please leave it at 100. You shouldn't go past 100. And then I'll put the content of that counter on PortC. It should not be a bad idea okay, let's start our project first. Then we'll know the next issues we're likely going to face. So I on the system. System is on. So the next thing I can do is to increment. So this is my increment. Now I've incremented. But if you look at it, this does not look like it's got 1. There is no 1. Higher. Are you there? Now this is not 1. What you have here, if I put up a calculator, I mean that is okay. So I don't have my Bible. I put on a calculator. I put up a programmer's calculator. What you have here is 100 into a controller itself and see what that variable has, what that counter has. Actually, the counter has 100. The question you're going to be asking me right now is, how did it get to 100? Hey, what is that is 100? Which means that our math was wrong. Let's see. Okay, so it would have gone the other way, coming. So it would have been 0, 1, 1, 0, 0, 1, 0, 0. Decimal, that would have been 100. That's what we should have done. Written it from here. Okay, so if you look at it, what this means is this. Let me explain what that happened. Excuse me. Okay. I'm back. So what it did was this. The moment this button was pressed, it went from 0 to 100. The moment the button was pressed, it went from 0 to 100. Why was that? That is because, let me explain to you. And we said that in class severally. We are running at 20 megahertz. The controller is using 1/4 of that as its internal frequency. 1/4 of 20 megahertz is 5 megahertz. The inverse of 5 megahertz should be around maybe 200 nanoseconds or thereabouts. I'm not sure, but it should be in the nanoseconds range. It means that this man is checking this pin every 20 nanoseconds. If it was 20 nanoseconds. If you imagine the number of that in a second, is huge. If we were using a 4 megahertz crystal, it would have been running at an internal of 1 microsecond. That is 1 million times in a second. So imagine the time it would have taken me to press this button and release it. It will have checked this button several times in a second, and that's the number of times it has reported to me. So what you should do in this case is that you are going to create something called a debounce switch or a debounce option. Debounce is such that you either create every time you press button, you create a delay. A delay enough time or enough time delay for me to have pressed this button and release my hand. So you create a debounce. So you either use a delay immediately after the instruction to scan when the button is pressed. The other thing you can do is to test when the button is released. So when the button is pressed, test when the button is released, which is what I ascribe to most times. So what I'll do is the moment it comes here, what I will ask is, I'll use the instruction while input that I will have scanned for. What I've done here is when that button is pressed, it is not going to okay, no, don't let me use this here. Let me first of all use the delay option. I don't want to be creating a class where you guys want to. So let's first create the delay option. So if it's equal to when this is pressed, if this is pressed, it should delay. Let's create a delay. Let's create a 2-second delay. 1, 2, 3. Let's create a 2-second delay. That will have been enough time for me to press that button and then release my hands from it. And then it can wait 2 seconds before it. It can wait 2 seconds before it does whatever it is it wants to do. This is just one way of creating a debounce switch. So let's look at it again. Let's go back to our simulation. Let's say run. And then this time I'm going to press this. 2 seconds after is when it's supposed to actually increment. So this is 1. Two seconds after. If I hit it again, it takes 2 seconds after to be here. This 2. If I press it again, it takes 2 seconds again to show me 3. So this 3. And when I press this, the same thing is done. That's 2. When I press this, it becomes 1. When I press it again, it becomes 0. So this was the assignment that I gave last week. Now, since I didn't have anyone who has done that assignment online, I've decided to actually get the assignment done. So this is the assignment. Again, if you look at it based on what I said last week, what we have done is very, very much in line with what we have been teaching. We've not used any syntax that is different from any syntax we've been using before. Simply to say, test the content of a pin, an input pin. The state of that pin is either a high or a low. Copy it into a variable. Test the content of that variable. The variable is 0 or 1, depending on your button state, whether it's active or it's active low. When the condition is true, what should you do? We have asked you to wait here. Maybe instead of waiting here, what we should do is to remove this here and then put the wait here, so that we know immediately that button is pressed. I mean, it helps. So we are not wondering, should I press it again? All of that will not be there. So it's the same thing. The project will still going to do the same thing. Except that this time, the moment you press it is when you see the action, you see the response, then before the wait. Let me explain that. And I ask it to run again. If I press it, you see the value. I mean, 2 seconds after is when I can press this again. So if I press again, it's not going to respond. You see, it didn't respond because it is still within the loop where it is waiting is 2 seconds. It is afterward that I can press again and it becomes 3. 2 seconds afterward is when I can press again and it becomes 2 seconds afterward is when I can press and then it becomes 5. So this is what the project is about. So this is how to design an up and down counter. This time we counted from 0 to 100 and then we decremented from 100 to 0.